In this video, we'll look more closely at the abstract problem of classification. In the previous video, we saw some examples of problems where machine learning can be used to solve them. And we also noted that we don't want to develop separate machine learning solutions for each and every one of them. And to avoid doing that, we translate the problems to abstract tasks with names like classification and regression, and then we develop algorithms for those abstract tasks. In this video, we'll see what that looks like in practice, and we'll focus primarily on the abstract task of classification. We also discussed in the previous video that supervised learning tasks are those tasks where an input and an output is given as an example for what we want to learn, and that classification is one of the two main supervised learning tasks. So, to classification. We start with some data. The data can be thought of as a large table containing examples of the sort of things that we want to learn. And in this case, the example we use is spam classification. So we have emails coming in, and for each email we want to classify, detect whether or not it's a spam email, so an unwanted marketing email, or what's called a ham email, a genuine email that we're interested in having in our inbox. Each row in this table represents one of these emails, an example of what we learn. That's what we call an instance. The rightmost column represents the label that we want to learn, the class. So we have two classes in this case, spam and ham. And the other two columns are features. And the features are the things we measure about our instances. So in this case, we might choose two words manually that are likely to be indicative of whether or not something is an email or not. And then as features, we measure how often those words occur in a particular email. So that gives us two features in this case per instance. That data set is fed through a learning algorithm, and the learning algorithm outputs a model. The model in this case is called a classifier because we're doing classification. And the model is constructed so that when it sees a new instance with the same two features that were in the data that we saw that we fed to the learner, a new instance for which we don't know the class, we can then feed that instance to the model, and the model will produce a class for us. And this is how the abstract task of classification works. We set up our data as this kind of table, we decide what our instances are going to be, what features to measure in that instance, and then we feed it to a given learning algorithm. So when we have a problem that we want to use machine learning to solve, the question is, where do we get our examples? What features do we measure? And basically, how do we build this table of data? And if we're a machine learning researcher building a new machine learning algorithm, the question is, given a data set like this, how do we build this learner? How do we build a computer program that spits out this kind of model? So we'll look at some examples of the first case first. Given a problem for which machine learning is suitable, how do we turn it into a classification problem so that it fits this framework? We'll start with the first of our examples from the previous video, that of digit recognition. How do we turn the problem of recognizing digits in zip codes into a classification problem so that we can solve it with any existing classification algorithm? Our first step is to reduce the problem to make it simpler. So we will assume that we are given an image of a single digit, and the task is to predict what the digit is. This is a much simpler problem than the overall problem of reading a zip code, but it's still a challenging one. And all the other problems, finding the digits, cutting them out, putting them in a rectangle, we'll leave that to other people to solve, possibly also using machine learning or just using traditional approaches. Then the second thing we have to do is gather a lot of examples of digits. And this is what a lot of people spent doing in the late 80s and early 90s, leading to datasets like this one. So these are all the 2s from a dataset called MNIST, M-N-I-S-T, which contains a lot of black and white 28 by 28 pixel images of digits, annotated with what digit they represent. So once we have these digits, we need to turn them into a table, like we saw before, of instances, features, and a target label. And the simplest way to do that is to take every single pixel in every single image as a feature. So every digit in our dataset becomes an instance, a row in our data. Every pixel in every image becomes a feature. The images are 28 by 28 pixels. So we just flatten out all those pixels into a long row, giving us 784 features, valued between 0 entirely black and 1 entirely white. And finally, we have one more column containing the 10 possible classes in this classification task. Because the picture represents either the digit 0, the digit 1, the digit 2, and so on. So there are 10 possible classes in this classification task. And if we do all this, we get a very big table, but one that we can feed to a learning algorithm. The learning algorithm produces a classifier, and to this classifier we can then feed a new digit, so long as we extract its features in the same way we did for the data, and then the classifier gives us its best guess for what it thinks the digit is that is shown in the picture. Another example, chess. As we said before, we have a lot of databases full of chess games played by humans, and we could learn something from them. So let's see how we can build this into a classifier. The problem of playing chess is not in itself a classification problem, so again we have to take the larger problem and reduce it to some part of the problem that we can solve using classification. And one thing we can do is use a classifier to predict from a given position on the board who is most likely to win. And to do that, we could construct a dataset a bit like this. So the instances here are positions on the board, so one chessboard with a particular configuration of pieces. From that we extract some features, and then the target label is to predict whether white wins in the end, black wins in the end, or it's a draw. And this we can take from our chess database. All these positions come from games, so we can look at the game, see who won at the end of the game that this position comes from, and use that to label the position with. And unlike the digits, this is not a perfect class. There is not one class that is absolutely true. From almost every board position, black can still win, white can still win, and it could still be a draw. But in general, we're hoping here that all these differences will average out, and the classifier will give us a good prediction for who is going to win from this particular position. A more complicated question in this setting is, what should we use as our features? One thing to do is to simply count the number of black pieces and count the number of white pieces. From that you can already, in some cases, give a very good prediction of who's going to win. If there are many, many more black pieces than white pieces, then black is very likely to win. But for a classifier that shows a little bit more insight, we'll need more features than that. And for this you can often look to domain knowledge. If you know a bit about chess, then you know that there are certain properties of a position that give an advantage to a certain player. Something like, if you own both bishops and your opponent doesn't, that's usually good for you. If you have a rook behind an open file, that's usually good for you, and so on. So all of these can be translated into features, added to the data set, and the more features and the better the features we come up with, the more information our classifier has to build on, and the better our predictions will likely be. In itself, this isn't a chess playing agent, but the classifications produced by a classifier like this can help us build better chess agents. For instance, we can take a classifier like this and build a search algorithm that looks for moves that lead to positions that we are likely to win. If you are familiar with the minimax algorithm, then a classifier like this would make a good plug-in heuristic value for the minimax algorithm. So we haven't used machine learning to solve the whole problem of playing chess, but we have used it for a component of the problem, which we can then plug into a solution for the larger problem. Our third example was that of a self-driving car, and here we can look at a very early system to learn to do just that, called the ALVINN system. This is a system built in the early 90s, and it used a very simple setup, a small camera mounted at the top of the windscreen, which provided a picture downsampled to 30 by 32 pixels, which captured the surface of the road, and then a sensor in the steering wheel which captured whether the steering wheel was kept still turn to the left or turn to the right. And driving like this in this car for a while, they captured a lot of data about the behavior of humans on the road, of human drivers on the road, which formed a classification dataset. So the instances are video frames from this camera, specifically pictures of the road surface, and they are labeled with the classes left, right, and straight to indicate how a human turns the steering wheel. As we did in the digit example, we simply take each pixel to be a feature and flatten out the image into a row of numbers. This leads to 960 features. And after collecting a bunch of this driving data, we have a classification dataset. I should note that I've simplified the classes a little bit. The original paper actually had more than 3 classes to indicate the precise angle of the steering wheel, but in general, this was the basic idea. So using a dataset like this, the authors trained a classifier and plugged that classifier into a driving system. And that system was actually able to drive coast to coast autonomously in America. They had a human driver executing the system's instructions, but otherwise they managed to fully autonomously drive in 1995 using such a simple classifier. So that's how we take a given problem, like recognizing digits, playing chess, or driving a car, and abstract it into a classification problem. The other side of the problem is, given an abstract task like classification, how do we design an algorithm that performs it? How do we build this learner? And how do we build the classifier that it produces? To illustrate this, we'll look briefly at 3 simple examples: a linear classifier, a decision tree classifier, and a nearest neighbors classifier. We'll only explain them briefly to give you a sense of how these problems might be solved, so don't worry if you don't totally get it yet. All methods will be discussed in more detail in later lectures. And the running example we'll use here is the one that we saw in the previous video of classifying the sex or gender of a given individual. We won't use pictures, we'll come to that sort of classifier later in the lectures. For now, we'll just take a bunch of people, and the features we will measure are simple biometrics. Specifically, we will measure their stature, which is a fancy word for their height, and their interpsi, which is a fancy word for the distance between the shoulders. So this doesn't tell us much about the person, but it should give us some information from which we should be able to predict their biological sex. Not perfectly, but with some measure of error. Note that, of course, this is a very crude example. Firstly, you cannot perfectly predict somebody's sex from 2 simple measurements like this. And secondly, not everybody's biological sex is captured by the classes male and female. We'll talk a lot more about this problem and what it means socially in the 4th video, but for now we'll just take this as a very crude example of how machine learning works. Now, the nice thing about a dataset with just 2 features is that you can plot it in 2 dimensions. So if we make the height the horizontal dimension and the distance between the shoulders the vertical dimension, then in those axes every instance in our dataset becomes 1 point, and we can color it by what class it has. And here we see our dataset, and we can see both that there is some rough separation between the 2 classes, but also that there's a lot of overlap, so that we cannot expect to get very good predictions based purely on these 2 features. But we can at least expect to predict better than chance level. So, using these axes, let's see how we can perform the act of classification. And the first example is a linear classifier. In other words, we separate the blue from the red dots simply by drawing a line. And we decide that everything above this line we call blue, i.e. male, and everything below the line we call red. So once we have this line expressed somehow, and we see a new value, an unobserved value that was not in our data, say somebody with a height of 170 centimeters and a distance of 45 centimeters between their shoulder blades, we can simply look where they are in this space, look whether it's above the line or below the line, and make that our prediction. In this case, it's above the line, so we predict we predict that this dot will be blue. In other words, we predict that this will be a male. Now, we chose just 2 features in order to make this process easy to visualize, but it's important to note that when you design a classifier, you cannot say that it's a classifier that works only for datasets with 2 features. We want classifiers to be generally applicable, so however many features the data has, the classifier should adjust to that. So we cannot say we draw a line, because a line only separates a two-dimensional space into two halves. So in order to make a generic classifier that works in all dimensions, we need to generalize the idea of a line to higher dimensions. And we can do that with something called a hyperplane. So a hyperplane is the high-dimensional analog of a line. Essentially, in one dimension, the linear structure that separates the space into two halves is a point. The space is separated to everything below and above the point. In 2 dimensions, it's a line. In 3 dimensions, it's a plane. The plane cuts the space into everything above the plane and below the plane. And in 4 dimensions, it's not easy to visualize anymore, but we call it a hyperplane. And it's a 3D linear structure that separates the 4D space, the space of 4 features, into everything above the hyperplane and below the hyperplane. Like I say, it's difficult to visualize, but the math is very easy. And we'll look at that in more detail in the next lecture. So now that we have a model, namely a line, the next question is, which line should we draw? So the space we've visualized so far with these features on the axis is what we call the feature space. And this particular model forms a line in that feature space. But the line we've drawn, the green one, is not the only line we can draw. We could also draw the orange line. So the next question is, out of all the lines we can draw, which one should we draw? And intuitively, it's obvious to us that the green line makes a better fit than the orange line, because the green line separates the red and the blue dots a little better. But we need to make this more precise so that we can build a computer program that selects this line for us. So the first thing to do is to define each line by a set of numbers. And one way to do that is this. We choose 3 parameters to describe each line. The first is multiplied by the height, the first feature. The second is multiplied by the distance between the shoulders, the second feature. And the third is added to that, not multiplied by anything. And using these 3 numbers, we built this formula, and the line is that set of points for which this formula is equal to 0. And this is just a way in which we can define a line in space. And depending on what numbers we choose for A1, B1, and C1, we get different lines. And this gives us the second space that we like to talk about in machine learning, the model space. So these 3 numbers, A, B, and C, define a line. So if we make those axes, then every line that we can draw is a point in that model space. So every point in the model space is a line in the feature space in this example. And our 2 lines that we see here, the orange and the green line, are 2 points in the model space. So now the question is, how do we search this model space for a line that fits our data well? And to do this, we introduce the idea of a loss function. A loss function is a function that expresses for a particular model how well it fits our data. So it's important here to see that whereas a model, like a classifier, is a function of the data that produces a class, the loss is a function of the model that produces a number that indicates the performance. And the data is part of the loss function, but it's a constant. So we vary the model to measure the loss. And the general idea of the loss is that the lower it is, the better the model is. And we'll look at a lot of different loss functions throughout the course, but for now, for classification, we can just use the number of examples in our data that are misclassified by the given model. So if we look at the orange line, we see that a lot of blue points end up below the orange line and a lot of red points end up above the orange line. These are all misclassified by the orange model. So the orange model has a very high loss, a very large portion of misclassified examples. And the green model also has some blue points below the line and some red points above the line, but far fewer. So the green model is a better model with a lower loss than the orange model. And you can visualize this loss function as something that colors every point in the model space. So the lighter the point in the model space, the more likely we want to be at that point in the model space. And we'll continue this discussion on linear classifiers in the next lecture. But for now, let's look at some other answers to the question of how we can build classifiers. Another structure we can use is a tree. This leads to what is called a decision tree classifier, which might look something like what we see here. The idea is that we start at the top, and at every node in the tree, we look at one feature, and we see whether it's higher or lower than a particular value. And depending on the answer, we move either to the right or to the left. So here we look first at the height of the person. If it's higher than 163 centimeters, we move to the right, and then we look at the distance between the shoulder blades and whether or not that is higher or lower than 42.4. And if it's higher, we move to the right, and if it's lower, move to the left. And at some point, we end up at a leaf in the tree, and all the leaves in the tree are labeled with classes. And when we end up with at a leaf, we simply label the example with that particular class. And for a structure like that, the coloring that we end up with in feature space looks like this. And the shape that any classifier draws in feature space to segment the two classes is called the decision boundary. So this is the shape of decision boundary that we get for a simple tree like this. In practice, these trees can get very complicated. So you might end up with something like this. We won't go into the details of how to find a particular tree to fit a particular dataset at this point. We'll look at that more when we get to decision trees in a later lecture. A final example is the k-nearest neighbors classifier. K-nearest neighbors is an example of a lazy classifier. It doesn't do any learning, it just remembers the whole dataset. Then, when it gets a new point, indicated here by the question mark, it just looks at the k nearest points that it already knows. In this case, we have set k to 7. It looks at all of those points, and it assigns to the point with the question mark the class that is most frequent in this set of neighbors. Simply saying, in this neighborhood of feature space, I'm mostly seeing blue points, therefore this new point is most likely to be blue as well. And here k is what we call a hyperparameter of the algorithm. This is a value that you have to choose yourself before you use the algorithm. We'll discuss how to choose hyperparameters in lecture 4. Here's what the decision boundary of the k-nearest neighbor algorithm looks like for our dataset. The new point from the previous slide is indicated in white. So, with that, we have seen 3 examples of real-world tasks that might benefit from machine learning that can be translated to classification tasks, and 3 algorithms that implement the abstract task of classification. There are a few variations of classification that we should briefly discuss. Features are usually numerical or categorical. So far we've only seen numerical features, but you can also use features that take values from a set of categories. Some algorithms only work on numerical features, some algorithms only work on categorical features, some algorithms work on both, and there are good methods for transforming a categorical feature into a numerical feature and vice versa. We'll look at those in the 4th lecture. The standard classification setting is probably binary classification, the case where you have 2 classes, but you can also have multi-class classification, the setting where you have more than 2 classes, like the digit problem that we saw earlier, and only one of them is true. This is distinct from multi-label classification, where we have a large set of labels and either none, some, or all classes may be true. This is a very different and very difficult setting, which we won't go into in this course, but there are ways to solve that problem as well. And finally, we've only looked so far at classifiers that spit out a single class, but it can actually be very helpful to have classifiers that give you a probability distribution over all classes, or if not a probability distribution, then at least a set of scores for every class, so that instead of just getting a single class that is predicted to be true, you can actually sort the classes by how likely they are to be true. This is a very helpful property for a classifier to have, and most of the classifiers that you'll encounter have this property. And of course, if you want a single class, then you can just take the one with the highest probability or the highest score. Zooming out a little, I hope what's emerged so far is that for offline machine learning, there is a kind of basic recipe that you tend to follow when you have a problem and you want to apply machine learning to it. The first step is that you look at your problem and you abstract your problem or part of your problem to a standard abstract task. And there are many abstract tasks available. We've seen classification so far. We'll look later at regression, clustering, density estimation, and generative modeling. There's also online learning, reinforcement learning, or structured output learning, which we'll look at less in this course. Once you've chosen your abstract task, You usually choose some instances and their features. And if you're doing supervised learning, you also need to have a target label for each of these instances. Then you choose a model class, which can be linear models, decision trees, or k-nearest neighbors. And then you somehow search your model space for the best model to fit to your data. And usually a model comes with its own search methods, but sometimes multiple search methods are available for a given model. And for a lot of machine learning, this basic recipe is followed. And here we see what that looks like in code. And you see that in a normal application of a machine learning library like sklearn, you do indeed follow these steps to train a model. In this case, the tree.fit method is where we search for a model that fits our given data well. So that's classification. In the next video, we'll look at some other abstract tasks, including regression, clustering, density estimation, and generative modeling.